Welcome. Today we're diving into the world of time complexity and algorithms. Time complexity is a fundamental concept in computer science that helps us understand how the runtime of an algorithm increases as the size of the input grows. Imagine you're sorting a list of numbers. How much longer does it take if the list doubles in size? Time complexity gives us a way to predict and compare the efficiency of different algorithms, so we can choose the best one for the job. Let's start by exploring why this matters in real-world programming and how it impacts software performance. Understanding time complexity isn't just for academic exercises. In real-world applications, choosing an efficient algorithm can mean the difference between a program that runs smoothly and one that grinds to a halt. For example, a search engine needs to process millions of queries quickly. If the underlying algorithms are inefficient, users will experience delays. That's why developers and engineers always consider time complexity when designing systems, ensuring that their solutions can handle large amounts of data without slowing down. Talk about time complexity, we use something called Big O notation. Big O gives us a way to describe how an algorithm's runtime grows as the input size increases. For instance, if an algorithm takes twice as long when the input doubles, we might say it's O(n). If the time quadruples, it could be O(n)2). Big O helps us compare algorithms without worrying about the details of hardware or programming language. It's a universal language for efficiency. Start with the simplest case, constant time or O(1). This means that no matter how large the input is, the algorithm always takes the same amount of time to complete. A good example is accessing an element in an array by its index. Whether the array has 10 elements or 10 million, retrieving one item takes the same amount of time. Constant time operations are the gold standard for efficiency. Next up is linear time or ON. Here, the time taken grows directly in proportion to the input size. If you have to look at every item in a list to find a value, that's linear time. For example, searching for a name in an unsorted list means checking each entry one by one. If the list doubles in size, the time needed also doubles. Linear time is common in many basic algorithms. Quadratic time, or ON2, means the time taken increases with the square of the input size. This often happens in algorithms with nested loops like bubble sort. If you have 10 items, you might make 100 comparisons. With 100 items, it's 10,000. Quadratic time can quickly become impractical for large datasets, so it's important to recognize and avoid these algorithms when possible. Logarithmic time, or O log n, is a big step up in efficiency. Algorithms with this complexity reduce the problem size with each step. A classic example is binary search, where you repeatedly divide the search space in half. This means that even for very large datasets, the number of steps stays manageable. Logarithmic time is highly desirable for searching and other operations. Linearithmic time, or O n log n, is common in efficient sorting algorithms like merge sort and heap sort. Here, the algorithm does a linear amount of work but also divides the problem, leading to the log n factor. This complexity strikes a balance between speed and thoroughness, making it ideal for sorting large datasets efficiently. Exponential time, or O2n, is where things get out of hand quickly. Algorithms with this complexity double their work with each additional input. For example, solving the traveling salesman problem by brute force means checking every possible route, which becomes impossible for even modest input sizes. Exponential algorithms are usually avoided unless absolutely necessary. Factorial time, or ON, is even more extreme than exponential time. Here, the number of operations grows as the factorial of the input size. This happens in algorithms that generate all possible permutations, like certain brute force solutions to puzzles. Factorial time is only feasible for very small inputs and is a clear sign that a more efficient approach is needed. Let's compare these complexities side by side. Constant time is always fastest, followed by logarithmic, linear, linearithmic, quadratic, exponential, and finally factorial. As you move up the scale, algorithms become less practical for large inputs. Understanding where an algorithm falls on this spectrum helps you make smart choices in your code. Time complexity isn't always the same for every input. We often talk about best case, worst case, and average case scenarios. For example, searching for an item in a list might be fast if it's at the beginning, best case, but slow if it's at the end, worst case. Understanding these cases helps you predict real-world performance more accurately. While time complexity measures how long an algorithm takes, space complexity looks at how much memory it uses. Sometimes you can trade one for the other. For example, you might use extra memory to speed up a calculation. Balancing time and space complexity is a key part of algorithm design, especially in resource-constrained environments. Let's look at a simple loop. If you have a for loop that runs from 1 to n, the time complexity is O(n). Because the number of steps grows linearly with n, this is the foundation for analyzing more complex algorithms, so it's important to recognize linear patterns in your code. When you nest one loop inside another, the time complexity multiplies. For example, two nested loops each running n times result in O(n)2 time. This is why algorithms with nested loops can become slow very quickly as the input size increases. Always watch out for nested loops when analyzing performance. Binary search is a classic example of logarithmic time complexity. By repeatedly dividing the search space in half, you can find an item in a sorted list much faster than checking every element. This efficiency makes binary search a go-to technique for searching large datasets. Bubble sort is a simple sorting algorithm with O(n)2 time complexity. It works by repeatedly swapping adjacent elements if they're in the wrong order. While easy to understand, bubble sort is inefficient for large lists, making it more of a teaching tool than a practical solution. Mergesort is a powerful sorting algorithm with O(n log n time complexity. It works by dividing the list into halves, sorting each half, and then merging them back together. This approach makes mergesort much faster than quadratic algorithms for large datasets, and it's widely used in practice. Recursion can make analyzing time complexity tricky. Each recursive call may spawn more calls, leading to exponential or even factorial time in some cases. It's important to break down the recursion tree and count the total number of calls to understand the true complexity. Memoization is a technique where you store the results of expensive function calls and reuse them when the same inputs occur again. This can reduce exponential time algorithms to polynomial time, making previously impractical solutions feasible. Dynamic programming often relies on memoization to boost efficiency. Sometimes an operation is expensive only occasionally but cheap most of the time. Amortized time complexity averages the cost over a sequence of operations. For example, appending to a dynamic array is usually O1, but occasionally, when resizing, amortized analysis gives a more realistic picture of performance. When analyzing algorithms, it's helpful to know the lower and upper bounds of time complexity. The lower bound is the best possible performance, while the upper bound is the worst. Knowing these helps you understand the limits of what's achievable and guides you toward the most efficient solutions. Asymptotic analysis focuses on how an algorithm behaves as the input size approaches infinity. It ignores constant factors and lower-order terms, letting us compare algorithms based on their dominant growth rates. This helps us focus on what matters most for large-scale problems. In big O notation, we ignore constant factors and lower-order terms. For example, O2n and O100n are both considered O(n). This simplification makes it easier to compare algorithms since the constants are often negligible for large inputs. When analyzing time complexity, always look for the most expensive part of your algorithm. Focus on loops, recursion, and data structure operations. Break down your code into sections and analyze each one, then combine the results to find the overall complexity. A common mistake is overlooking hidden loops or recursive calls that increase complexity. Another is misjudging the impact of data structure operations. Always double-check your assumptions and test with different input sizes to confirm your analysis. Consider a web search engine. It must process billions of documents quickly. Efficient algorithms with low time complexity are essential to deliver results in milliseconds. This is a prime example of how time complexity impacts user experience on a massive scale. The choice of data structure can dramatically affect time complexity. For example, searching in an unsorted array is O(n), but in a hash table it's O1 on average. Picking the right data structure is as important as choosing the right algorithm. Hash tables are a powerful data structure that offer O1 average time complexity for insertions, deletions, and lookups. This makes them ideal for tasks where speed is critical, like caching or counting occurrences in large datasets. Linked lists allow for efficient insertions and deletions, but searching for a value is O(n) because you may have to traverse the entire list. Understanding these trade-offs helps you pick the right tool for each job. Balanced trees like AVL or red-black trees offer O log n time for insertions, deletions, and lookups. This makes them a good choice for maintaining sorted data and supporting fast searches, even as the dataset grows. Algorithms that operate on graphs like Dijkstra's or BFS have their own complexities. For example, BFS runs in OV plus E, where V is the number of vertices and E is the number of edges. Understanding these formulas helps you estimate performance for network and relationship data. Let's compare some common sorting algorithms. Bubble sort is O(n)2, mergesort is O(n log n, and quicksort is O(n log n on average but O(n)2 in the worst case. Knowing these differences helps you choose the right sort for your data and needs. Quicksort is a fast sorting algorithm with O(n log n average time, but it can degrade to O(n)2 if the pivot choices are poor. Randomizing the pivot or using median of 3 can help avoid the worst-case scenario and maintain high performance. Divide and conquer is a strategy where you break a problem into smaller pieces, solve each one, and combine the results. Many efficient algorithms like mergesort and quicksort use this approach to achieve better time complexity. Greedy algorithms make the best choice at each step, hopping to find the global optimum. Their time complexity varies, but many are efficient, like Dijkstra's shortest path algorithm. Understanding the complexity helps you know when greedy methods are practical. Dynamic programming breaks problems into overlapping subproblems and solves each just once, storing the results. This can turn exponential time problems into polynomial time, making complex tasks manageable. Examples include the Fibonacci sequence and knapsack problem. NP-complete problems are a class of problems for which no efficient solution is known. Many famous problems like the traveling salesman and subset sum fall into this category. Understanding their time complexity helps set realistic expectations for what computers can solve efficiently. When exact solutions are too slow, heuristics and approximation algorithms offer practical alternatives. They may not guarantee the optimal answer, but they run much faster, making them useful for real-world problems where time is critical. Parallel algorithms split work across multiple processors to reduce runtime. While this can dramatically improve performance, analyzing time complexity becomes more complex as you must consider communication and synchronization overhead. In practice, optimizing time complexity often means profiling your code, identifying bottlenecks, and choosing better algorithms or data structures. Sometimes, small changes can lead to big improvements in performance, especially for large-scale applications. Imagine sorting millions of records in a database. Using an ON2 algorithm would take hours, while ON log n sorts finish in seconds. This real-world case shows why understanding and applying time complexity is so important for scalable systems. Time complexity is a key topic in technical interviews. Candidates are often asked to analyze and compare algorithms, demonstrating their understanding of efficiency. Mastering these concepts can give you a strong edge in job applications and coding challenges. To wrap up, time complexity is a crucial tool for understanding and improving algorithm efficiency. By mastering Big O notation, analyzing different cases, and choosing the right data structures, you can write code that scales and performs well in any situation. Keep these principles in mind as you tackle new programming challenges. Now that you have a solid understanding of time complexity, the next step is to practice analyzing real algorithms. Try breaking down the time complexity of your favorite sorting or searching methods and experiment with different data structures. The more you practice, the more intuitive these concepts will become, helping you write faster, more efficient code.